Imagine your car's battery is literally sitting in a bathtub, and that saves it from catching fire. Sounds wild, right? What this video is about and why you should care about this. Today we are diving into a technology that could change how electric vehicles stay cool, charge fast, and maybe most importantly, stop battery fires from spreading. I'll explain how liquid immersion cooling works, why engineers are excited, what the hard problems still are, real companies and studies already testing it, and whether this bathtub for batteries idea is the real fix or just another clever experiment. By the end, you'll know if immersion cooling is hype, hope, or next big thing in EV safety. Hello everyone, I'm Shayan, an engineer specialized in electric vehicle development. Batteries in EVs are awesome at storing energy, but not great at handling heat. Inside every lithium-ion cell, chemical reactions release heat when you charge, discharge, or push the car hard. If one cell overheats, it can trigger thermal runaway, an uncontrolled chemical chain reaction that makes temperature skyrocket and can cause the cell to vent, burst into flames, or make neighboring cells fail too. That cascade is why a single failing cell can lead to a full pack fire and why firefighters and engineers are terrified of what happens once thermal runaway starts. This problem has driven decades of research into better battery chemistries, smarter pack designs, sensors, and cooling systems. So, how immersion cooling actually works? Think of immersion cooling like putting each battery cell into a special bathtub filled with dielectric fluid. The liquid touches the cells directly, so heat transfers away fast and evenly. That removes hot spots, keeps every cell at similar temperature, and helps stop one overheated cell from cooking its neighbors. Some systems fully submerge cells. Others use near full or partial immersion to avoid contacts with certain parts of cells like tabs. The key is the liquid must be electrically safe, chemically stable, and good at moving heat. The advantages are big on paper and in lab tests. Much better temperature uniformity across the pack, which boosts battery life and performance. Fewer hotspots mean less stress and longer cycle life. Faster heat removal during ultra-fast charging so you can push higher charge rates faster and safely. Potential to slow or stop thermal runaway propagation because the liquid absorbs and carries the away heat and can physically limit flame spread. Pack designs also could be simpler and denser because you don't need bulky air ducting or heavy cold plates between cells. This isn't just lab talk. Automotive and energy companies, startups, and researchers are testing immersion cooling in real battery modules and even in prototype vehicles. Racing and niche EV makers are early adopters because they push batteries hard. A notable example is a sports car maker partnering to use immersion-cooled packs in a prototype vehicle. Large oil and gas and chemical firms are also developing specialized dielectric fluid optimized for EV use. That's a sign the industry sees commercial potential, not just academic curiosity. Even if immersion cooling reduces temperatures, there are several big challenges before it's on every car. Long-term chemical compatibility between the coolant and battery materials. Seals, casings, sensors, adhesives, everything needs to survive years submerged. Maintenance, repair, and recycling complexities. And what happens when a pack needs to be opened in a shop or recycled at end of life? Cost, weight, and packaging trade-offs for mass-market vehicles, and the fire behavior under the real-world crash or abuse conditions. Does immersion always help? Or are these scenarios where it makes things worse? What about regulatory and safety and emergencies responder training changes? How do firefighters handle an immersion-cooled pack? Here's the myth. Thermal runaway spreads when a hot cell heats its neighbors faster than they can dump that heat away. Immersion changes that math. Direct contact with coolant dramatically increases heat transfer coefficient. The fluid carries heat away and spreads it across a larger volume, reducing the peak temperature experienced by the adjacent cells. Some immersion fluids are engineered to suppress flames or limit oxygen contact, further slowing combustion. In controlled tests, full immersion modules have shown blocked or delayed propagation in many scenarios compared with air or traditional liquid cooling systems. Now let's go a balanced list of pros and cons of this. For instance, the pros: it has faster and more even cooling, it supports higher charge rate, lower cell stress, and longer life. Possible range and durability improvements are there. and it reduces risk of fast propagation of fires. The fluid absorbs heat, dense packing is possible, and the cons are new failure modes and chemical compatibility questions will be rising. Seals and sensors must be robust. Maintenance and recycling complexity increases over time. First responders and technicians need new procedures. Cost and supply chain for dielectric fluids and new manufacturing techniques are needed. Industry adoption at scale is not guaranteed as well. Imagine a team racing to build a prototype EV that charges in 10 minutes. They're pushing cells hard in a tiny pack. Temperature spikes, and air cooling can't keep up. The team switches to immersion. Within minutes, the pack runs cooler, charging metrics improve, and the team breathes easier until they realize the gasket material under long term thermal cycling is swelling. That single material choice could make or break a program. It's a reminder thermal wins are great, but materials engineering is the gatekeeper. Several real lab reports and industry tests show these exact trade offs. If immersion cooling proves reliable in the field, the ripple effects are huge. Faster public charging without frying batteries make EVs more convenient and closer to ICE refueling times. Smaller or lighter packs for same energy, improving range per weight. Lower long-term warranty costs from fewer thermal-related failures are there. And new vehicle architectures where batteries are packaged differently, enabling design freedom here. Several peer-reviewed studies and industry pilots from 2023 to 2025 have demonstrated improved thermal uniformity, effective cooling during high-power events, and even suppression of flame propagation in bench tests. That doesn't mean every fire problem disappears, and it's a major step. But what the data and the studies actually say? Let's be concrete. Reviews of battery thermal management show immersion cooling ranks high for heat removal and uniformity compared to air and conventional liquid cooling. These reviews compile many experimental and CFD studies. The experimental papers show immersed cells can survive hotter, faster charge cycles, and that some immersion strategies block thermal propagation in lab setups. But these are controlled tests. Real world validation is ongoing. Industry pilots and press releases indicate early adoption by performance and niche OEMs and active development of specialized fluids for large suppliers, hinting at industrial momentum. But large-scale mass-market adoption still faces cost and regulatory hurdles. Emergency responders and safety regulators look at EV fires differently than car designers. There are established guides that recommend how to fight EV battery fires, and they often involve lots of water, immersion, or prolonged cooling because batteries can reignite. If manufacturers switch to immersion-cooled packs, responders will need new protocols. Immersion is similar but not identical to current methods, and tools and trainings must adapt. Some official guides already discuss soaking or applying water to EVs. Immersion pack vehicles would change the details. A few things people assume that deserve a quick reality check. For the myth, if a battery is submerged, it can't catch fire. Not true. Immersion reduces risk and slows propagation, but some chemistries and conditions can still produce venting, smoke, or fire. The fluid changes the behavior, it doesn't magically eliminate chemistry. Another myth, immersion makes repairs impossible. Not necessarily. Systems can be designed for serviceability, but it will be requiring new standards and safe handling protocols. Here's another myth. This will instantly make EVs cheaper. It is unlikely. Initial costs may risk due to new materials and manufacturing changes. Cost reductions may come later if the benefits allow smaller pack or lower warranty costs. So what needs to happen for immersion cooling to go mainstream? It needs long-term durability testing across many climates and miles, standardized fluids that are safe, recyclable, and available at scale, pack designs that are repairable and meet crash safety rules, clear rules and training for emergency response and recycling, economic models showing total cost of ownership benefits for car makers and buyers. Several researchers and pilot projects are already tackling these questions. There are variations worth knowing. Short technicals aside, there are different types of immersion. Direct full immersion, cells completely go underwater in dielectric fluid. Partial or near full immersion. Parts of the cell are kept dry and protect tabs or connectors. Spray or mist cooling. Fluid is sprayed onto cells rather than bulk immersion. Each approach trades off heat transfer, complexity, and risk in slightly different ways. Lab work show full immersion gives the best cooling, but partial immersion can reduce electrical or maintenance headaches. So does immersion cooling solve the EV battery fire problem? Short answer is yes. It significantly reduces many of the drivers of battery fires, hotspots, uneven temperatures, and fast propagation. Lab data and early pilots show real promise, but it's not a single magic bullet that erases all fire risk or manufacturing complexity. For full confidence, we need more field data, long-term durability, crash tests, repair and recycling workflows, and standardized emergency procedures. The best framing is this: immersion cooling could be a major new tool in the box that combined with better chemistries and smarter pack design make EVs safer overall. What to watch for next? Pilot programs by mainstream OEMs rolling into production models, publication of long duration field tests showing no unexpected corrosion, swelling, or seal failures, clear emergency responder guidance for immersion cold systems, new standards for recycling and fluid reclamation. These indicators will tell us whether immersion is moving from promising lab tech to real-world game changer. Liquid immersion cooling changes the physics. It takes heat away faster, evens temperature, and can blunt the spread of thermal runaway. That reduces fire risk and opens door to faster charging and denser battery designs. The trade-offs are material, maintenance, cost, and new safety practices. The most honest prediction: immersion cooling will be part of the EV safety and performance evolution. Not the single silver bullet, but it's probably one of the most important steps we have seen in battery thermal management in years. Here's a quick checklist you can remember. Faster cooling leads to better charging potential, but check materials compatibility. Better temperature balance leads to longer battery life, but check sealing and serviceability. Slower propagation leads to lower fire risk, but check real-world crash plus long-term tests. Technology rarely fixes everything at once. Immersion cooling looks like one of those smart, practical fixes that, when combined with smarter chemistry, better sensors, and safer pack design, could make EVs noticeably safer and more convenient. The next few years of field testing and standards work will tell us how fast this moves from prototypes to parking lots. If you want to go deep in the battery management system and learn about its algorithms and how it's working, you can click on the link in the description for the BMS course. Thank you.